Hi, students. At least in first period, I neglected a very important bit of instructions or a bit of example for the accelerated motion lab using vernier video analysis. So I wanted to make a video explaining what to do in the end of the lab where I'm asking you to use data from the raw data or from the graph of velocity versus time to find out how the acceleration changes with time and to plot acceleration versus time. So I'm referring to 7C, D, and E. Using graph paper or a spreadsheet app, use at least some of the data points for your velocity from your velocity versus time graph or raw data to plot acceleration versus time. And then explain what you had to do in order to plot acceleration versus time. And is your plot what you expected? So first, let me show you the data I'm working with. And if you had problems accessing vernier video analysis, as we are continuing to have problems with vernier accepting our embedded key, please email me and I can share this data with you. But I collected data for one of my own videos. This was a steel ball bearing rolling down, I think it was a 14-inch high, 2-meter long track. And so here is a graph of position versus time. This is the graph of position versus time. And that then I fit to first a linear fit. So I'm saying, does this work as a linear equation model? Are these linearly related? Or are they better quadratically related? And I think it's pretty clear just qualitatively that more of our raw data fits along the quadratic line than it does along the linear line. So I believe that the best fit for this data is a quadratic function. And so we have the quadratic fit details there saying that we're fitting this data to an equation or to a mathematical model of the form y equals ax squared plus bx plus c with those values in the box for a, b, and c. Then I switched my graph to show velocity versus time. So here is the velocity versus time graph for my ball rolling down the hill. It's not as clear what the graph shape here is. And that will be the case for all of our data for this lab, no matter what your video is. And that's because for every data point of velocity versus time, the computer is actually calculating change in position divided by change in time for each pair of position data points. So for whenever I'm not clicking exactly in the middle of the ball, or when the frame shot for the ball is blurry, I'm introducing error in where the ball is, which then gets compounded when we calculate change in position divided by the time interval. So we see velocity values that are clearly gaining. They're clearly rising here as time goes on. The velocity is clearly, in general, getting bigger. And I could definitely see how this data could fit a straight line, with some of the data being too large and some being too small, but a good amount being equally too big and too small. And I don't see much of an improvement in how much data is above and below the fit line when I look at the quadratic fit. So I go for the easiest or the most simple relationship between the two variables that seems to be a good fit between the two variables raw data. So I think a good fit for this is a linear fit, even though it's definitely less of a good fit than the quadratic fit was for position versus time. So I think this should be a straight line. Relationship of the form y equals mx plus b with the values shown for m and b, m being the slope. And m here would represent the rate of change of velocity or the acceleration. So this mathematical model I'm suggesting says that the acceleration, which is the slope of the line of velocity versus time, is 8.303 centimeters per second every second. So in number 7, I ask you to look at the raw data or to pick data points from the velocity versus time graph. I found it just easier to cut and paste the data table. This is more data than we need, right? We're only looking at what the value of velocity is at what times. We don't need the raw data for X or Y or for the Y velocity, but here's your raw data, cut and pasted. And again, the question is, using graph paper or a spreadsheet app, use at least some of the data points from your velocity versus time graph to plot acceleration versus time. So here's that data in Excel spreadsheet form. And again, we're ignoring position in the X direction, position in the Y direction, and velocity in the Y direction. We're only looking at time and velocity. And the idea behind this is that we define average acceleration as change in velocity divided by time interval. And the way you actually calculate that is to say, what's the velocity at some point in the future, I'll call it V2, minus what's the velocity at the earlier time, what's the ending velocity, what's the starting velocity, divided by how much time has elapsed. So I go back to my data table and I say, okay, well, what if I found the average acceleration from 0 seconds to 1 second? So at 0 seconds, I have a velocity of 4.9123827. So I'll say V1 is equal to, let's just round to 3 digits, 4.91. And then at 1 second, the velocity is 12.16. So V2 is 12.16. And so acceleration is V2 minus V1 divided by T2, 1 second, minus T1, 0. So acceleration is equal to, and wherever is my calculator, 12.16 minus 4.91 divided by 1. Oops, I mistyped that. 12.16 or 12.2 minus 4.91 divided by 1 second. So 7.25 centimeters per second. That's interesting because my mathematical model, wrong page. Where did that go? My mathematical model for a linear fit said that the acceleration should be 8.303. So this is not horribly different from 8.303, 7.25 centimeters per second versus 8.303 centimeters per second. It's a little lower, but it's, not totally out of the ballpark. So this is the idea. I can pick 2 times from my data table, and for those 2 times, find the corresponding 2 velocities, and calculate average acceleration. In order to plot that, of course, you need to have more than one average acceleration calculated. So I used Excel in this section to find the average acceleration from 0 to 1, 1 to 2, 2 to 3.067 because I didn't have a 3.0, 3.067 to 4, and 4.493. And I just asked Excel to do that calculation. So here's what I asked Excel to do. So Excel does D5 minus D2. So D5 minus D2 divided by A5 minus A2. And we get a value of 7.2469, right? We rounded in our hand calculation to 7.25. So again, from 1 to 2, 1 second to 2 seconds, I've done D8 minus D5. So change in velocity divided by A8 minus A5, change in time. Okay. And so you can see for each almost 1 second time interval, I've calculated that average acceleration, again, using our equation, for average acceleration here. And so I have 1, 2, 3, 4, 5 calculations for average acceleration. So I could potentially plot 5 data points. The problem here is that this is the average acceleration over each of these 1-second time intervals. So how do I plot a time interval? If I took smaller and smaller time intervals, I'd get closer and closer to a moment in time, but I sure don't want to program Excel to do that. So instead, I just decided to plot the midpoint of each of these time intervals. So I'll plot 7.25 centimeters per second at 0.5 seconds, because that's halfway from 0 to 1. I'll plot 8.43 centimeters per second for at 1.5 seconds. And so that's what I have down here. I also rounded those acceleration values because I didn't want to deal with the string of decimals. So I turned this into a graph. In fact, perhaps, well, no, I'll just leave it like that. So here is acceleration, or average acceleration, every 1-second interval plotted at the midpoint. So here, starting at 7.25, between 0 and 1, perhaps a bar chart would be appropriate for this. Here I have 8.43 from 1 to 2 seconds. Here I have 8.91 from 2 to 3 seconds, 12.4 centimeters per second for 3 to 4 seconds, and negative 0.263 for 4 to 5 seconds, so almost 0. So what this looks like is maybe acceleration actually increased for most of the time the ball was rolling, and then decreased to 0. Somehow at the end of the track, the ball seems to have stopped accelerating. However, throughout the ball's motion, if I look at these average acceleration values, I'm betting that if I took the average of these 5 values, I would get something pretty close to 8.303 centimeters per second. So it looks like acceleration does change as the ball rolls down the track, but it looks like the average acceleration for the entire trip is pretty close to the acceleration predicted by my linear fit. So that was the idea for part 7. If you're in period 1B, you do not need to include that as part of your lab report, because I did not get this information to you in time. But for periods 3B and 4B, I expect you to analyze your own acceleration calculations for your own data. Again, as always, please don't hesitate to email me with questions, come into office hours with questions, and I'll see you after Martin Luther King Jr. Day. Bye.